Welcome to Unit 11, Lecture E. We're talking about organic reactions today. Organic reactions are going to be slower than the inorganic reactions because we are breaking covalent bonds and reforming new ones, so it's going to take more energy. We tend to use pretty strong catalysts and heat to help that happen. We are changing the functional groups, not the carbon chain. The hydrocarbon chain itself often stays exactly the same, and that's why in previous lectures I told you can figure out which alcohol and aldehyde was made from just by changing the ending group for the functional, because the reaction itself doesn't change the carbon chain. In substitution, we are going to be working with saturated hydrocarbons. So these are going to be our alkanes. We are switching some of the hydrogens for something else. So for example, if we had propane, there's no room to add anything else here. It's saturated, it's full of hydrogens. If I wanted to add some kind of halogen to that, I would actually have to remove a couple of the hydrogens first. So if I removed a couple of hydrogens, I would have room then to add my bromines. And we call that substitution because we're substituting the bromine for the hydrogens. When we do halogen substitutions, the products are called halides, and we've talked about halides on reference table R's, the very first category. These bromines would be named the same way you would a carbon branch, and table R says the branch name would be bromo. In addition, we're going to be working with unsaturated hydrocarbons. So we are going to be looking at molecules with double or triple bonds in them, and we're going to break those bonds. So if I had a molecule with double bonds, and I were to add bromine, this time the double bond is going to break, and we have something like this. Now this leaves us with two spaces, and that's where your bromines are going to go. And we don't have an additional product over there. So we've just added bromines to our molecule and saturated it. When we use hydrogen to do this saturation, then we call it hydrogenation. We use bromine specifically to check to see if we have an unsaturated hydrocarbon, if it has a double or triple bond, because this original hydrocarbon will be clear, the bromine's a reddish color. If there's double or triple bonds, it's going to go back to being clear again, so we can see that. Remember, substitution saturated, addition for unsaturated. Fermentation should be familiar to you from biology. This is where we're going to let yeast convert sugar into ethanol. The simplest sugar that they use is the glucose, because that's essentially what the other ones will break down into. You'll see yeast on the arrow. Sometimes you'll see the zymase enzyme also written on the arrow. When they make the ethanol, the other byproduct is going to be carbon dioxide. And then, of course, that equation would need to be balanced. But sugar turning into ethanol and carbon dioxide is fermentation. This was a good way to store calories in a form, make disinfectants. We use the carbon dioxide from this process to make our bread rise. Fermentation's been used throughout history for quite a while now. Recognize the equation itself, and I know I wrote it in the wrong place, but stick it into the blank down there for yourself. Esterification is going to be the production of esters, remembering that the general formula for an ester is COOC, and that we said this first half came from an acid, which is COOH, and the second part came from the alcohol, which is a hydroxyl group. The hydrogen from the acid, the hydroxyl group from the alcohol make your water, and then the leftovers make your acid. Um, it's called dehydration. Remember that the part of your ester that has the double bonded O and the other O came from the acid, so we can figure out which acid and which alcohol any ester was made from. So if I say I have pentyl propanoate, you know that the alcohol it was made from would be pentanol, and the acid that it was made from must have been propanoic acid. If you need more reminder than that, go back to lecture D and watch the ester section. Esters are artificial flavors, artificial scents. They're made naturally by flowers. Fats are esters, hormones are esters. The scents and the taste can be pleasant or unpleasant. They are an extremely important group of molecules. Saponification is going to be the formation of soap. So we're going to take fats, which are various different molecules and usually very, very long, plus a very strong base. Typically, you're going to see sodium hydroxide here, turning into our soap, which will have one nonpolar end and one polar end, which is going to help it to dissolve both polar and nonpolar products, which lets us wash them off with water. Otherwise, things like oils wouldn't wash off of our hands or our clothes because the water, being polar, wouldn't dissolve them. And your other byproduct is typically glycerol. This is going to be the easier one to pick out. It's the trihydroxyl alcohol that you've memorized earlier in this unit. So the base and the glycerol will be the easiest ones for you to pick out. Just know that saponification is the name for forming soap. Oxidation is a broad category. When we are doing oxidation of hydrocarbons, then we call it combustion. They're all exothermic. I want you to find them on reference table I. There's a list at the beginning. In the simplest one, when we have methane gas in lab and we're adding oxygen to it, we get carbon dioxide and water. When you have complete combustion, then you have only carbon dioxide and water left over. So that's going to be complete. If you have incomplete combustion, then your byproducts can be carbon monoxide or even just plain carbon. Polymerization is going to be the formation of very large molecules, and these things can be of infinite size by repeating smaller parts that we call monomers. So individual names linked together into these very long names. So two ethylenes put together would be polyethylene, because you could have any number of these units. Typically what they would show you is, N ethenes turning into ethene, N linked together. There are lots of naturally occurring polymers like proteins. Their monomers are amino acids. Cellulose, their monomers are starches. Starches, their monomers are sugars, etc., etc. We also make tons of synthetic polymers, all of our nylons and plastics, anything that you see poly in front of, PVC pipe, all of these things are going to be polymers. What is special about polymers is because once they're made and they're one giant molecule, they're extremely durable. So latex paint, when it's wet, is a bunch of small monomers. When it dries, it links itself together into one giant molecule on your wall, and now your paint is scrubbable and washable and much more durable than it would be if they were individual pieces. In condensation polymerization, you're removing some part of each monomer to link them together. In addition, polymerization, you are breaking a double or triple bond. Polystyrene is puffed up with gases, typically CFCs, to make styrofoam. And PVC is a very common polymer. That's the white plastic pipe that we use for plumbing. What's special about that is when we put it together, we don't use a normal glue. Glues and epoxies are polymers, but in PVC they use a solvent that actually opens up the bonds within the plastic itself, and when you put the two pieces together and the solvent evaporates, it allows them to re-link together back into one giant molecule. So all of that white plumbing in your house is actually one big molecule. Moving on to petroleum. Petroleum is a mixture of hydrocarbons. It's not just one molecule itself. They split that mixture through a refining process by doing this fractional distillation. So they take the mixture, they put it in a fractionating column, so it's a big giant column where they heat everything up until it all vaporizes. As it cools, density and their different condensation points will let them condense out at different temperatures in the cooling tower as it cools off. They take those fractions and then further refine them through more distillation until they get as pure of a mixture as they want. Gasoline is still a mixture. A lot of the greases, kerosene, fuel oils, they are still mixtures and not just one individual hydrocarbon, but they typically have a high percentage of a hydrocarbon that we want. The gasoline, the highest percentage in that is usually the octane. So the octane rating will tell you what percent is the molecule octane. They have another process called cracking, where large molecules that maybe wouldn't be of value to us can be split and broke into smaller molecules that would be valuable to us. Like we can increase the octane rating in a gasoline by cracking some of these larger molecules into the smaller 8-carbon chains. The biggest takeaway for petroleum is to understand that it is a mixture and that we use distillation to separate out the separate fractions.